So let's look at the law of sines. I want to do a quick derivation of the law of sines. There's a lot of situations where the law of sines comes in. There's a lot of different variations of how you use it, but we can derive it by imagining we know one specific we're trying to solve one specific practical problem. So we have a triangle. It's not necessarily a right triangle. This C looks pretty close to a right angle, but it's not, and we're not going to use that in any special way. One of the great things about the law of sines, and we'll see about the law of cosines, is they expand trig to beyond just right triangles. That's the real point here. So suppose we have a situation where we know angle A here and angle B, and we know just one of the sides. We know, let's say, side B. So that's the data we know. And we want to know more about the triangle. In particular, just very specific question, I just want to get side A. So first of all, is it plausible that we might be able to do that? Well, if I know how long this is, I like to think of this in terms of physical terms. Maybe like this is the ground, this is some slanted rod planted in the ground up to some point up here. And then I want to know how long it's going to be. Like I'm going to take a rope maybe and connect it down to the ground over here. And I want it to be at a specific angle here, and I know this angle and I know this side, well, that's really going to determine exactly how long the rope is going to be. So it's reasonable to imagine that A is going to be determined somehow. Okay. Now, as I said, this isn't about right triangles right here. That's the only way we know how to get trig into a picture like this is to have right triangles. So what we're going to do is we're going to drop a perpendicular. Let me just go ahead and have Sketchpad do that. Excuse me. I'm going to try not to cough too much. So we're going to construct a perpendicular line. Let me go ahead and just kind of cut that off to make it a little prettier. So I'm just going to do that only. I'll hide this. Okay, and maybe I'll put that as a dotted because that's not really part of the original data. Um, oops, or dash, let's say. Okay, but it's really crucial. Okay, so I'm going to label that. This is lots and lots of law of sines problems. We really end up talking about the height of a triangle. And of course, that's super, super important in a lot of things. So that's the height. So again, if you're thinking of like this is a beam, this B is a beam stuck into the ground, and I want to know how to connect it, it's very reasonable to think, well, I probably should know how high above the ground that is, and that'll give me some idea of how long the rope is that's going to stretch down to the ground. Okay, so what have we done? We've dropped an altitude. Basically our universal thing. If you're stuck on a geometry problem, draw more stuff and probably drop an altitude. Probably put in some sort of perpendiculars. Okay, so that suggests we've now got two right triangles, the left-hand right triangle and the right-hand right triangle. We totally know how to do trig with that. And so it suggests that we could get H and then use that to get A. And indeed we can. Okay, so in the left-hand right triangle, we know that over H over B, that's opposite over hypotenuse, and that's going to be sine of that angle A. Okay, so in other words, as is very, very often, we clear the fraction, and we get one side, the opposite side is hypotenuse, oops, times sine of the angle. Very, very common form of just the trig ratio. Okay, so let's see. I've got that down here. I went ahead and calculated the sines of A and of B because we're going to need B in a minute. B sine A, 3.81 centimeters, and I can check that. Let me just have it measure the length of that segment. You bet, 3.81. Okay, so it's working. Okay, so now what else do we know? So now the right-hand triangle. Okay, same deal, different letters. H over A is sine of B, because that's if we look at this angle here, it's still opposite over hypotenuse in that new right triangle. Okay, so now, well, what do we want to solve for? Well, let's clear the fraction anyway, because that's really standard to do. But here, we want to get A. Okay, so A is going to be H over sine B. Now, we could write that with a cosecant, but nobody really does for various reasons. I'm not sure exactly why. I mean, there's good reasons. It looks prettier with the signs, but you could. But anyway, it's going to be H over sine B. Great, you know, we're almost done, because we know that H is B sine A. And we're basically done. Okay, let's check it out. I had Sketchpad calculate that for me. b sine A over sine B is 7, and indeed A was 7 all along. Okay, so it really is working. I'm not making this up. Okay, so this is one form of the law of sines. Notice it's called the law of sines because only sines actually come into it. Okay, there's a couple of other forms. One is where I put all the A's together with the sine A on top. So what I do is let's see, multiply by, actually that's kind of a cool form, but you don't usually see it written that way. But one form is to get all the A's together and all the B's together on different sides um, with the signs on top. So just manipulating the fractions, not doing anything more fancy or original than that. Or you have the flipped version. Sometimes it's convenient to have this with the lengths on top. Doesn't really matter. Almost any problem you do with law of sines, you're going to have to do some sort of manipulation with the fractions anyway. So you don't want to think one is like much better. Now, a couple of things. That's really the essential thing. There wasn't really anything special about the fact that I was using A and B here. I could have done the same trick with C and dropping another perpendicular, and so you get the very same situation with like relating A and C or B and C, and that's one reason why these forms are really nice, because it's not hard to believe if C has a totally symmetrical role here, then in fact all three of these things are going to be equal in both cases. So that's cool. So it's a very pretty rule. This is probably the most common way you'd see the law of sines written out. That doesn't mean you have to use it in exactly that way, but it's probably the prettiest way. The other thing to note is, notice I did this in a situation where that angle A was acute. Ooh, and it's not really having a lot of fun drawing that perpendicular anymore, unfortunately. But it turns out, excuse me, that it still totally works here. Look what happens here. B sine A over sine B, that's how we were calculating A, 11.68 centimeters. It's still right on the money, even though the picture looks a little different when that angle A is obtuse. So it works for any triangle. Acute, obtuse, even works for right triangles. It's just, it actually kind of defaults back to our usual understanding of sine. So in the next video, you'll see use of this with an ASA situation. It's a little bit different what I've shown you here. Cool.